this class? Zen and
We have totally 8.
8.
So except Thai, but we have another student, Huda. I'm not sure, she from the Saudi Arabia.
Oh,
She took, maybe she took 622 with Snadish, I do not know. So I did curious. She took the theoretical mechanics, but remotely, since she was sick last semester.
Yeah.
So I'm not sure she will come in class or still remotely. Yeah, good, thank you. So,
cook, Zen,
Yeah.
Shay.
yeah, she, Zen and
Cook.
Kale.
Okay.
Thai moved, right?
Yeah.
Yeah,
He went for computer science.
computer science. Good. Maybe he likes computer science.
He is very expert in computer.
Yeah.
Typing all the
That's
commanders.
the beginning. Last semester, I look his roster is from speed school. And then he said, I'm physics. So I think I come back, I'll see, yeah, I change to the physics. Then now I change back to
Yeah.
speed school.
Yeah.
Yeah,
He's very indecisive.
yeah.
It's quantum mechanics too. Gonna be twice the fun, twice the work, twice the stress. Twice the difficulty.
It's better than the theoretical mechanics, right? From your exam, the exam.
Mhm.
Yeah, a lot of homework or practice the textbook show, right? So you can help learn
Yeah, yeah.
independently. But theoretical mechanics do not have too much
Yeah.
example to do the practice. Each one is a little complicated, so that's different.
Yeah. Goldstein was a bit stingy
Yeah.
right there.
Yeah. So I give you the solution. You're okay,
Yeah,
right? So
yeah,
I just
yeah.
try to see if you have any question. You can still discuss if you want.
Yeah, could I come by take over the quantum? I feel good about the
Sure.
class.
Yeah,
now.
yeah,
Thank you.
Your quantum is over there.
Oh, okay, okay.
Yeah,
I haven't been
in your
here.
mailbox. I saw it's still there.
Okay, okay, I'll go over there.
Example. Discover. I think he already took. You already took. Yeah.
He is a clever guy.
He's very smart. How was your holiday?
Ah, that was good. How was yours?
It's awesome.
So much
My
snow.
brother came to visit me.
Oh.
Really? So your brother from where?
He is currently in Ames Lab.
Oh, Amsterdam.
Yeah.
Okay. So he drive here or he flew here?
He came to visit me.
Yeah, visit you the drive or because snow?
By bus.
Okay.
His flight was cancelled due to weather.
Yeah, that's it. Yeah. Oh, that's good. You have a brother there. So also physics?
Yeah.
Wow.
He's doing now his postdoc research in Ames Lab.
Oh, okay. Okay, good. That's why you came to the States?
Yeah.
All right, let's, I'm not sure why, but I think it's time, right? Yeah, let's, I think the syllabus is fine. I also post on the Blackboard, so you're all fine if they miss. Yeah, somehow confused, maybe you got the email at January 2nd.
Mm.
Because it's very strange that there's another user ID, M0, YU0002, M1. So by some of a mistake, they enrolled he to this class as an instructor, but that person already left. I guess that was a student from Speak School. So I couldn't get into the Blackboard, I couldn't do nothing. Then I asked the Blackboard service, and they say they cannot do. They have to wait and ask Missy. She helped me, so then I finally come into. Hi, you're
Hello.
welcome. Hello.
How are you?
I'm fine. How about you?
Good.
Good.
How was your break?
Break is good. Just stay at home. Otherwise, yeah.
I was gonna say you sounded like it wasn't even a break. Break?
Break? It's still break.
What was
I'm
when did
thinking
that happen?
You know, I work on this. I want to make this all as a PDF file, so I spend the time in the break. So you say, I'm take a rest? Yes. You will say. So do you know the Zhang? He's coming?
He's on his way, yeah.
Okay.
He was getting everything together.
All right. Okay. So just quickly go through the syllabus because you're familiar with syllabus. Just select different. I just try to. So today just go syllabus. Then we are going to start to the spherical harmonic. Spherical coordinates. Right? We already start from chapter 6 plus 3D, and now we are going to deal with if the potential cannot be separated into x, y, z. So those are I think textbook same thing, and let me see, reference the same. Now I think here I want to this one. I think the meeting hour changed because this semester I have teach thermal, which is a noon time. So for the Tuesday, Thursday afternoon, I'm okay in my office. So if you want to stop by, and you can visit my office or just send email to me, contact me. Now, I think I did this one last semester, but I still want to do that. Hello? I think this is in case. That's why I always wear the mask to be safe, so I can teach without miss any class, right? So in case, since winter we know a lot of virus, flu, if I'm sick, so I cannot come, then I'm going to go to the Blackboard Ultra Club. You know this one before? Maybe new student, you know, right? You both. Yeah, I already set up. So if you go to the Blackboard, you can see here in this column, you can see this one. If in that case I will announce, and you click here, and I'm going to set up this the section. The specific day, then you log in here, so I can teach online and in the same time, same class time. So that is what I just want to mention again. In that case, I hope probably not. And yes, so now this is what we are going to cover, the second part of quantum mechanics, right? We are going to finish chapter 6, is a 3D dimensional problem. We already deal with the if the potential can be separated into x, y, z components, so we can separate this Hamilton equation eigenvalue problem into the one dimension x, y, z, right? But if not, then how to do that? So we're going to discuss the spherical coordinate. Sorry. One of the important example application is hydrogen atom. Then we are going to discuss if we put the hydrogen atom into non-field. So you will see the so-called Zeeman effect. Then we are going to discuss how the Zeeman effect comes from. After that, we are going to discuss rotation. In chapter 5, we already introduced the angular momentum, right? So now we are going to discuss in general the rotation in the quantum mechanics, how to describe rotation, what is the rotation operator, and if we have several angular momentum add together, how to deal with this 2-particle or 3-particle with a spin or with angular momentum. This part, if we do not have time, we just as optional. Then chapter 8. Before chapter 8, we always deal with single particle, right? So a single particle with spin from chapter 7 and without spin. But now we are going to discuss with many particle system. So in that case, if the particles are identical, if are identical, we are going to deal with the symmetry of the permutation or exchange of the particle, what kind of symmetry. And that symmetry will deal with why we have the fermions or bosons. That's corresponds to that symmetry. Then as an application, we can briefly discuss the periodic table by applying the Pauli exclusion principle. Now, this we have, this is a many-body problem. Then now we go to chapter 9, is we're going to deal with this perturbation. That means chapter 4 and chapter 6, we just consider the Hamiltonian, we still can solve analytically. But if we consider even complicated case, we have to use the perturbation theory. So that is the chapter 9 for time independent part how to deal with the predication theory or variational principle. That is the chapter 9. Then chapter 10, consider time dependent. So before chapter 10, we always deal with partial h, partial t equal to 0, right? Does not depend on time explicitly, but if depend on time, how to deal with. So in chapter 10, we're going to cover those. Then depend on time, if we can have enough time at the end of this semester, I'm going to discuss that. So I put optional because last semester I do not have time to hear, only to hear. So let's see, how much we can cover. So that is the topics we are going to discuss this semester for quantum mechanics 2. Homework, same thing as you're familiar with last class, that the last semester. Every 2 weeks I'm going to assign homework, so you do the practice. And due date, I'm going to announce that. Then they still encourage you to do as a group. You can discuss each other. Then the homework will be graded, right, as a part of the final score. Now, the exam also has 2 exams, midterm exam and final exam. And announcement usually 1 week before. Similar as last semester, the midterm is only take home. So I can have more time to discuss the class, the topics. That is one thing. And that is during this break between 8 and 20. So 8 is the last class between break, so I'm going to deliver and then your turn on this day. The final exam, also like 50%, take home and in class. So again here, this in class we are going to fix when we reach to that day, right? So this one is the last day of our class. I'm going to give you this take home final exam. Participation, similar as last year, last semester. I'm going to use the participation sheet to monitor your participation. And the last semester, all of you did a good job. I mean, either you have something, you just email me so I know what happened, or you just attend the class without any absent without excuse, right? So that is the policy here. And this policy for this grading also the same as last year, so you can have this percentage and cutoff. Okay. So again, this cutoff is tentative. I probably can maybe lower this cutoff. You know, this year, last semester I lowered a little bit, right? So maybe the same, but I did not raise the cutoff. This day, I think next Monday we do not have a class, right? That is not to lose holiday. Then the break here, right? Break is 13 to 19. The last class, then we are going to assign our final in-class exam in this period, right? That is, okay, I think the others same as before, so I'm going to close this. Any question? All right, now let's start it. Okay, just briefly remind. We solve the time independent Schrodinger equation, right? In this case, the Hamiltonian has a 2-part kinetic energy. Then if the potential energy can be written in terms of this x components, y components, and z components. Then, since this one is Laplacian, right? So that is minus h bar square. Oh, okay, all in the position representation, right? Okay, so here we know that is also already separate. So if the potential separate, then we have the Hamiltonian can be separated into the x components part and y and z. Then this one, the time initial equation is reduced to, I think we already described that, remind you since after the break. Right, so now we have x components. Okay, so the wave function r can be written products of the three, right? Then here, for x, for y, and z. Each one just 1D problem, right? That we already discussed in chapter 4. So that is the end of last semester, we even in one of the exam, right? So we know once we have this potential can be separated into these individual components, then the Hamiltonian can be separate or separable. So the time initial equation is met. Then when what we solve, so final energy is Ex plus Ey plus Ez, right? And this wave function here. Then we solve each individual depend on the potential along this x, maybe the harmonic, along y, maybe it's the infinite square potential well. It depends. So that is case. Now let's consider if the potential r cannot separate, right? Example. Some potential example like this. This is an isotropic harmonic oscillator, right? Does not depend on, there is no direction of the particular direction, is any direction the same. So this is isotropic harmonic oscillator. One case. Or we have, if we have, this one is very simple, right? So this is the high energy. Or Coulomb potential, right? Let's just say Coulomb potential in general. Coulomb potential energy, or let's just do this one as two examples. So you can see here, the R is only depend on R. R is square root of x squared plus y squared plus z squared. So we have, that is y, right? So this is that is y. Then how to do that? So now we are going to see how to deal with this type of problem. Here, this is absolute R, right? So that is means they have a spherical symmetry. The potential has a spherical symmetry. And we know central force problem, right? You already took this theoretical mechanics. We learned the central force problem, the different type of central force. But if the central force, the potential also central, that is only depend on the magnitude of R. So that is this case. Because this R is the square root of x squared, y squared, z squared. So we cannot separate. Then now this is our job. So that is from today, we are going to deal with the solidity problem in the spherical. Because this is spherical, we know this R is one of the coordinates, right? And theta phi. So that means we can use that is solidity spherical. Okay. So the question comes from the potential symmetry. So now we're going to deal with this. Now the question is, since this is 3D, the complicated here, right? We have this the different directions, so different paths. Then if we cannot separate it into this way, how to deal with to make this one is doable. So now the key is we are going to see here, right? The Hamiltonian, how to rewrite, right? Rewrite Hamiltonian such that we can separate this time-Schroding equation into R-dependent part or angle-dependent part. If that's possible, so now let's do that. To do this, first we know that let's look this Hamiltonian. Hamiltonian, I just derived the traditional representation, right? Now here, this is R, right? I already used this spherical symmetry. So the key is here. This potential and the function depend on R. If in the spherical, so this part, if we can write or rewrite it not in terms of x, y, z, but in terms of R theta phi, then we will substitute this into this equation in here. So that is the first job we are going to look at this one. This one in spherical, this is a Laplacian, right? Spherical coordinate. And this, I think you know, so I will not derive how to derive that, I just give you the part. Okay, so if you know that is 1 over R squared partial R squared partial R, and plus 1 over R squared sine theta partial theta sine theta partial theta, and plus 1 over R squared sine squared theta partial squared partial. Right, so this we know. Okay. Now I'm going to rewrite this way. Separate into radial part and angular part. Okay. So how to separate? Okay. So you can see here, this one, the radial part, is this one. Right? That is 1 over R squared partial R squared partial R. Or it's really depend on which way, because it depends on different type of potential here. We will take this one, or second one, the result in that. That is definition. that is the Laplacian and the radial part, right? Then this part, there are two types. Is that possible? You can see?
The, not the last line, but the one above it.
This
What's
is
your
cool.
subscript? Where you were, but what's your subscript? I can't.
Omega,
Omega.
called
Okay.
capital Omega. Yeah. Okay. Either this way, they are equivalent. You know equivalent, right? Do I need to prove they are equivalent? Okay, then before to prove that, let me explain a little bit. Sometimes we use this one, sometimes we use this one. The reason is depend on potential type. And we are going to see to match which special differential equation, which you learn in the what is mathematical physics. You learn several special differential equation, right? So keeping this one, maybe sometimes we use this one. So that is I usually use this too. So the proof they are equivalent. Let's start from here. The second one, the R, 1 over R partial square partial R square R is equal to 1 over R partial R. And the first partial, partial R this way, because we do not have usually we need another function here, so now partial R. So this one actually is first do R, so we have 1, and second one we keep here.
Okay.
That makes sense? Yeah. This is not the only partial R, it's partial R with some other function. So then you can see here. Okay. Then you do second, right? Do again, so you have this one is, sorry, yes. Then here, this one still partial R here. Then we do this one again, we have another partial R. When you do this one, so you remove this one, right? And then plus R partial square. So here we have a twice. Then I'm going to write 1 over R 2 partial R plus R partial square partial R square. Now here, I multiply R square here, then I have R square, right? From here. I multiply, this is a 2, factor 2, but then I divided R, then I have to multiply R here, right? So here that is 1 over R square, 2R partial R square partial square R partial R square. Then here this is not, any question? Here is this one. You do this 2R, right? Partial, then so they are equivalent. So that is R square partial R. That is, so these two just let you to familiar with these two, depend on which case we are going to use one of them. That is the radial part, and then this delta omega square is the angular part, right? Because this we have a 1 over R square. Take 1 over R square outside, so that is the main part. Is 1 over sine theta partial theta sine theta partial theta, and 1 over sine square theta partial square. Okay, when we introduce these two, you can, okay, before we go back to here, we want to understand the physics of this. We introduce this as a Laplacian project to the radial direction part. So what is the physics? Physics of these two, right? let's first, since the Laplace written in two half, let's look. That is the physics of such this. So in order to understand physics, we first define or introduce, we call the radial momentum operator. PR is half of R hat. Okay, that is unit vector. P hat plus P hat R hat. We call this radial momentum operator. Now, if we introduce this one, we are going to prove this PR can be written into this way. Is minus IH bar partial R plus 1 R, or minus IH bar 1 R partial R. We are going to prove. And this again, these two formula like this, two different types, depend on which case. But usually we are going to use this one, that one. This is a Hermitian. Since we introduced the momentum operator, when we say that is this operator corresponds to the physics quantity momentum, must be Hermitian operator, right? So we can prove it is. You can prove yourself. If it is. Now we are going to prove this equal to this definition, right? And this be equal to this. Now let's do proof now. And then we're going to find what is the relation between the radial momentum operator and this radial Laplacian. Okay. Because we know the momentum operator here, right, is a vector, we know this minus IH bar gradient. We know this, right? And this one in spherical coordinates, in this Cartesian, we know that is a partial x, partial x plus partial y plus partial z, which is a vector, right? I, j, k, three components. But in spherical coordinates, we know this is equal to r hat, right? Around r hat, the component is partial r, and around the theta hat is 1 over r partial theta, around this phi hat is one over r sine theta partial. So we just substitute into here. So now let's do this. We are going to find the operator. We are going to find this PR, the PR hat operator equal to this, right? So how to do that? We are going to use the function, arbitrary function, to help us, right? Look at this. If this PR, this is the operator applied to any function f. Now what this means here is minus RH bar, this one, right? So that is this definition here. This one, right? Half of R hat P plus right definition. Then this P is here. Right? This P operator is minus IH bar, the gradient. So now we are going to substitute this half. Since we have a minus, so now let's take this minus IH bar outside, minus IH bar. Okay. Now inside. So here, this one is this one, right? So then we have R hat dot, first one, right? R hat and partial. I'm going to put f of the end, right? partial R, this one, and plus R hat dot theta hat, 1 over R theta. Partial theta, and plus R hat dot phi hat, 1 over R sine theta, partial phi. This one is this term. So we have 3 terms, right? R theta phi, right? In the product. And then this one, plus. Here I also took minus alpha outside, right? So then they became this is here R hat partial R with dot inner product is R plus second one theta hat 1 over R partial theta inner product is R. Yes. And phi hat 1 over R sine theta partial phi inner product R hat. Then the F. So be careful is where the R is in front of this gradient or after that. If after that we have to take this derivative. So that is be careful. Okay, so first this term R hat dot in hat is 1, right? So that is non-zero. But this one, since they are perpendicular, this is 0, right? So now we have to keep here. This one is only the term. This one, right? Because this is equal to 1. And this was 0, so that is plus 0, plus 0. Second term, third term, 0. Now come to here. So here we need to know we have an F here, right? So actually this is a partial R hat F. So you have R hat partial R hat inner product partial R, right? This term. And then plus R hat inner product R hat partial F partial R. We have 2 terms, right? This R hat multiply F. So this partial R is partial, the product of R hat with F, so we have 2 terms, right? This, that makes sense? Okay. The next one is this term. This term, again, we have a theta hat, 1 over R partial R hat partial theta. This is also inner product because it's a 2. And F plus, so when this keeps in theta hat over R and inner product R hat and partial F partial theta, right, is this. The last one, phi hat 1 over sine R sine theta and partial inner product partial R hat partial phi F plus phi hat 1 over R sine theta and inner product R hat and partial F partial phi. Okay. That makes sense? Now you can see here, we are going to use, we need to know this one, right? Partial R hat partial R, partial R hat times theta, and partial R hat partial phi. This, if we remember that, let me just write down, try to help you to remind this relation, this partial derivative of this unit vector. Partial R hat partial R is 0. Partial R hat partial theta is theta hat. Partial R hat partial phi is sine theta phi hat. So now we are going to see, keep continuing here, right? This one is still here. So now minus I h bar over 2 partial. Okay, I think I need to put F here so that I already put in, right? So here this is F. So partial F, partial R. Now this one, because partial R hat, partial R 0, right? So this term again 0. Now we do not have this one. Now come to here. This R hat is 1. So now we have another partial F, partial R, right? This term. This one, partial R, partial theta is theta hat. Right? Partial R hat. So theta R hat is 1. So that is R. This one. This one, inner product 0, right? So there's no this term. And this one, partial R hat, partial phi is sine theta phi hat. So phi hat independent of this cell. Then we have sine theta cancel. So we have minus R F. Last one, phi hat inner product R hat 0, right? I think this. So finally you have a 2, this, right? So 2 cancel. Then we have minus I H bar partial R plus 1 R F. Now the left hand side is PRF. The right hand side is this operator multiply F. So that is this one. Right? We got this. Then we got this, so you can, this is very easily to prove this, since this one is easily to equal to R partial R F. Since you know if this one is partial is 1 plus partial F partial R. 1 over R, if we put inside, right, 1 over R, and R cancel is this term, so they are equivalent, right? These two are equivalent. That is why we put here. Okay. Once we have this, but this one we cannot see. We cannot see the relation between the radial momentum operator and this Laplacian operator around the R part. So we are going to see this one, PR square. Okay. We know PR, so PR square. Again, we are going to use F to help. PR, let's use this one. Is equal to minus RH bar, 1 more R, partial R, right, this one. That is square. I didn't do the exact square because be careful, since this one, if we have R is after this partial derivative, you have to do the partial derivative. So that is be careful here. Then here, minus plus, I is minus, so we have minus and plus here. Then we have one of the R is here, right? Then partial R. This inside is R. Okay. If I use this one, this is a cancel, then this is a partial, same thing, right? So we have a 1. Okay. So you see here, we have R. I have R. This cancel, right? This is after this derivative, but before this one, so they cancel. Then this is became this one is a partial. Is this term, right? Okay, then you can see here I do H bar square and R partial R. I do this one first. I do R, so that is partial R is F plus R partial F partial R. Then I keep continue. So 1 over R, and do this is partial F partial R plus partial F partial R plus R partial square F partial R square. Okay. So we have minus h bar square 1 over r 2 partial r plus r partial square partial r square f. And this one is equal to, very easily you can see that one is equal to partial 1 over r square partial r square partial r f. Or, as I said, the equivalent is 1 over r partial square partial r square r f. Then you can see, oh, did I erase? Remember this one, right? This one is nothing but this. Okay. Right? I just erase. So we can easily find the relation between this Laplacian So finally we can find the delta r squared is equal to minus 1 of h bar squared p squared. So that is directly related to this radial momentum operator, square radial momentum operator. Okay, that is the physical meaning of this r squared. Then the physical meaning of this delta omega squared. Now, if you remember the angular momentum, chapter 5, in the spherical coordinates, expression is this one, right? 1 over sin theta partial theta, sin theta partial theta, plus 1 over sin square theta partial square partial phi. Remember this. Then you compare with these two, you will see this difference, just this minus h bar squared. So this delta omega square is minus 1 over h bar square angular square. Now we can go back to our Hamiltonian. Now we can rewrite our Hamiltonian in the spherical coordinates if we introduce the radial momentum operator. So finally, Hamiltonian is write on the origin, right? And we can rewrite h bar square m since this Laplacian operator is written in two parts, right? Radial part plus 1 over r square omega square, right? Then now we are going to use the relation here. So that equal to minus h bar square over 2m. Here, that is minus 1 over h bar square p r square minus r square, so that is 1 over h bar square m square. Then you see here minus h bar square cancelled. This one also cancelled, so we have r square 2m r square. See, now I rewrite the Hamiltonian in this way. And you can see this way we are familiar. Now, only this p is not the linear momentum operator square, but it is PR, it's a radial momentum. So this term is kinetic energy, we call radial kinetic energy. and this one angular. Kinetic energy. Operator, right? You can say operator or energy. This part is potential. Okay, so now if in the spherical coordinates we can rewrite Hamiltonian into these three terms. If in the Cartesian only two terms, right? One is kinetic energy and that's potential. But in spherical we separate into the radial kinetic energy and rotational. Okay, now rotational. Kinetic energy and potential energy. With this way, now we are going to look if we can separate this or rewrite this Hamiltonian into different way and try to see if we can find or solve the eigenvalue problem here. Now, before we do that, let's look this one. So this is the final expression of Hamiltonian, right? With this one, now let's look this. We're going to solve here. Since I already use spherical coordinates, now this r theta phi equal to E. This is we are going to solve, right? Solve this one. And solve this one here. We are going to follow the same idea when we deal with the Cartesian. If it's separable, we can deal with this equation by only one of the coordinates. So let's see if we can. Okay. So first, we are going to analyze the behavior of this wave function. If it's separable, the wave function is a product of different parts, right? So now let's look at this one. The potential commute with angular momentum. Yes or no? Potential only depends on r. Angular momentum is only a function of the theta and phi, right? So they commute. And definitely this also commute with LZ, because LZ also only the function. One is r radial part, another is angle, separate. So that is first. Then you can see this one. About this one. This one we know that is only radial part, right? So the PR square also only the radial part. Then it will independent of any angular part. So this also commute. I use square actually. If this, then what that means? Let's look at Hamiltonian. Hamiltonian is L square. So Hamiltonian is this three part, right? PR square plus L square over 2 R square plus VR is L square, right? Since L square commute with PR, L square commute with self, right? L square, and L square commute with R. So yes. Similarly, the Hamiltonian also commute with LZ. If this case means they have a joint eigenstates, the joint eigenstates should be a kind of the radial part, which we are going to solve. So I'm going to use R as the radial part, but separate with the angle, right? Because they are separate also, the Hamiltonian separate with the angular momentum. That means the wave function should be product of the angular part and the radial part. The radial part we do not know. That depends on different type of potential we are going to solve. But the angular part we already solved in chapter 5. So we know this is the angular momentum, right? So that is okay. Here we deal with optical angular momentum. Since here this is considered the rotation. when we extend to the spin, or generally that is, we are use this, the direct notation cat, right? So here, since we are in the spherical coordinates, then we just immediately use here. So now this is a very important here. If this is separable, we are going to put this into here. Then you can see we can derive the, or reduce that equation to radial part, since angle part we already solved. We only need, the question is, this is unknown, right? This is unknown. And the angle part we already know. That is why we separated study in chapter 5. Focus on the angular momentum. That makes, we know, then when we deal with 3D, it makes us easier. Okay, so now, let's see how to do that. If I have this wave function can be written in the product of the radial part and the angular part. In particular, we know the angular part is the eigenstates of the L square, right? L square, this is a spherical harmonic. Chapter 5, who remember, is h square L, this angle, the eigenvalue, right? H bar and M, right? Yes. Okay. Now we substitute this Hamiltonian into that equation, so we have okay, keep PR, let's keep PR. So PR square 2M plus L square over 2MR square plus 3R. This function here. I didn't use index here for R. That later we're going to discuss. What kind of index associated with this? But we know the index or quantum number for the angular momentum is L and M. So now we are going to divide this products of the function both sides. Then we have this one is PR square R. I'm going to move this outside since PR only depends on R, right? Let me give R1 and this one. Divided by N R. Plus here L square R and YLN 2MR square plus VR equal to E. Since we divided by this product, this is equal to 1, right? So that is okay. Now let's look at the first term. This PR square only, if you remember that this operator is only works on the R radial part. Does not have relation with this one, right? So this can take outside. This take outside, then they cancel this one. So the first term is reduced to right? Second one, this one I can also take outside because L square does not any relation with the R part, the radial part. So I take R function out in front of the L square, and L square apply this. While Lm gave us h bar square, so we have divide. And then R cancelled, right? And this one also cancelled. And lastly, equal to E. see here, this only depends on R. Now let's rewrite this one, then you can see finally we reduce this eigenvalue problem over time independent Schrodinger equation for 3D to for kind of 1D only radial part. The angular part we already solved. So finally, if I multiply the R function both sides, then you have P square R for 2n plus h bar square L plus 1 4n square R plus 3 Now I'm going to substitute this PR square, the operator which we derived before, right? Then we can see this is a partial, second order partial derivative. So now, remember that is 1 minus h bar square 2m here, right? And the 1 over r, remember? 1 over r partial square partial r square r. This is the operator for PR square. Here we have a minus h bar square, right? Okay, then this one, we keep it. So now I'm going to move. Still keep it. H bar square. Now I'm going to divide this minus h bar square over 2m to both sides. So this one it became positive. This one have a negative. Then I move this term to the left hand side. So finally we have 1 over r partial square partial r square r multiplied with r function plus 2m over h bar square. Now the energy moves to here, right? The minus plus, so that's energy minus this term negative h bar square, so 2m, so we have only the L. Oh, we take h bar outside, so this is L. Yes, we have that because there's no such thing as h bar square. 2n is outside. Okay, this one cancels, so we have 2n, so I have to also divide by 2n. And 4 minus v equal to 0. Here, this one, I use one of the expression for this PR square, right? We can have another one, or so finally we have another one, or we use 1 over r square partial r, and r square partial r, and the remaining part same. The only difference is the first term. I didn't have any special with potential here. If you want to have R. This is called the radial. We're going to solve R. Since when we solved R, we can have this solution. fine. This is sometimes we may use this one. U R is R multiplied. This is in circuit mechanics. You chapter 3. You remember we also sometimes introduce U, right? Because the differential equation for U is easier to deal with instead of R. So either use this one depend on the potential, and maybe use this. So if we define this one, you can see here. I'm going to, so this is a, you can use this one better. So this is a U, right? This is a U. And then you take one of R here, then you have a U. So now let me just do it. So we have this one. Let's square that one. You are. Yes, here we have R, multiply R both sides. So this one come to here, so that is U, right? So that is very simple. We have a partial square U R, partial R square, plus 2M, H R square, E minus, H R square L, L plus 1, 2M R square minus 3R. U are equal to 0. Or we introduce effective potential. E minus A effective potential equal to 0. Here we define effective potential is this two terms. Right, in chapter 3 is theoretical mechanics. We also deal with, of course, this central force problem gave us a different type of potential, but we know this term. This is a positive, right? Positive term. That means repulsive. Repulsive potential. Here. This is the potential. The real potential may be repulsive, may be attractive. We do not know. But this one we definitely know. And this one also depends on the orbital angular momentum, L. So if L equal to 0, no contribution. If L is not 0, we know when we do the rotation, there is also always associated with centrifugal the force. That potential is correspond to this repulsive. Okay, so see if I use U, it became very simple, right? So that is second order partial derivative of U with this energy minus the effective potential. So that differential equation. But it is again depend on if that effective potential is easier to deal with or not. So the effective potential, since you learned this theoretical mechanics chapter 3, we know this here, right? This is a real potential VR. Suppose, right? Example, if the VR is this Coulomb force, or we know this force follow this inverse square law. So we know that is potential is negative, attractive. Then we know this term. The repulsive is always positive, depend on L, right? So here. This is H bar square L plus 1, 2M R square. Also decay with R increase. And finally, combination of these two give us the effective potential. And we know there's a minimum here. I mean, R minimum means this position or equilibrium position correspond to this minimum potential. So if this is the case, we know there is always a bounded state. The particle will stabilize here. And this minimum, this increased L will become shallow and shallow, right? And also the minimum position also increase, right? That is what happened. Okay, so that is the behavior of radio in general we have discussed. Then our next job is to deal with this one. This is a very important, and also this is the only differential equation we are going to deal with for 3D if we have a spherical symmetric potential. Then how to deal with is really depend on this one. The different type of potential give a different type of differential equation. Then we are going to manipulate it to see whether it is, if we can solve, that we can try to find the solution if it is follow this some special differential equation. Let's see here we have something now. Let's brief discuss. This is a general, right? We haven't discussed detailed potential, so this is a general discussion. First, I think this one is already here. This behavior. That is we already discussed here, right? So that is the first issue we will discuss. The second one, let's look at this one. So R here. You see, this differential equation depends on L. If L different, the term different, right? Then if you solve the solution, to find this one, you may get another quantum numbers. Remember, we know that when we solve this eigenvalue problem, we will have introduced the quantum number to categorize states. So for this radio equation, they depend on two quantum numbers, L and some others. The other one, I'm going to introduce it, N. Right? So that means and another quantum number. That's called N. So we do not know, we have not solved each individual, but we know from this differential equation, we need to determine which L. For given L, you will have one solution, right? And for that solution, you will have introduced another new quantum number, so we are going to give N. So what that means, after the solution of R to depend on NL. We are going to, that is later we are going to introduce Y. So when you write down here, this instead of R now is RNL. But we giving L will solve, and then we are going to have the quantum number N. That is the behavior of this. So if you have this, then the wave function, the solution or joint eigenstates for this Hamiltonian and angular momentum here, now we can rewrite is R and L, right, index, and Y L N. So here I'm going to use N L N. The wave function depends on these three quantum numbers. That is, we do not know the details, but we can analyze at least it depends on L, does not depend on N, right? From this equation. So that is, we introduce the two quantum numbers. I mean, that is the radial part depend on this. Okay, that is the that is second. The behavior of this solution depends on which quantum number. Then we so far we have not discussed spin, right? If we include spin, so then this if I use this this one is spin. If it is a total wave function of the particle considered spin, so it has this radial part and spin part. Spatial part and spin part. Spatial is function r theta phi, so that is be n, l, m, and the spin. Spin here, let's use s, m, s, right? So here is the spatial part. Is the spin part. We know spin independent of the spatial coordinates, so they can be products. That is, so in the later when we deal with the system, say we have to consider spin, then you are going to solve two jobs. First, solve this one, then the spin may be half, or maybe 3/2, maybe 1, maybe 0. You also need to solve this, and the final solution is product of these two parts. That is, from now on, we have, since we already introduced spin, so we can deal with the system if we have a spin. Okay, now let's consider the degeneracy of energy. I just erase because the radial function is I just right radial equation for right. This is for define energy, right? We solve this energy. It depends. I say depends on n and l, right? What does mean? Independent of m. Because I just erased that part. The radial equation you can see only for given L, and we are going to solve. Then we have a new quantum number is n, but whatever the m is, no m means. So what that means? Energy only depends on two quantum numbers if we have a spherical symmetry. So if the system potential has a spherical symmetry, we know there's a degeneracy. How much is degeneracy? How much? For given L, we have 2L plus 1N, right? At least this. And there are more. Maybe more, it depends on different type of potential, but at least. At least 2L plus 1 is given. Since here, that is here. Since for this wave function, for given energy, we have 2L plus 1 m values. 2L plus 1, the wave function corresponds to same energy. So that has degeneracy. I think let me just quickly finish. Number 4, number 5. Number 5, we are going to normalize this wave function, normalization of NLM. Since we know this quantum system, the wave function always characterizes this system of the quantum or particle, right? So it basically asks us to be normalized or to be finite. That means we are going to normalize here. One is r from 0 to infinite, and another from the solid angle, the whole solid angle. So we have NLM. Then we have r squared dr and d omega. Right? So then we know it is separate, a product of two, so we can integral r part only, that is r and l. And only the angle part is this spherical harmonic function. How much is chapter 5 is 1. We already know, right? It is already normalized. So that means this normalization only or take care of non-radio part. And by physically it's equal to 1. Right? This is a very required. So what that means? That means this integral r, the r is in the range from 0 to the infinity, but the function r is finite. Must be infinite. That is number 5 from this. Okay, let me keep the last one. The last one is to discuss the possible solution of the radio equation, which since you already learned, did you learn the conflict, hypergeometric conflict differential equation? Yes, that's good. Generally, it's that one, but depending on different potential, the solution different. So next, we are going to discuss different type of potential, like free particle, isotropic harmonic, and the hydrogen atom. You will see the differential equation. The solution will different. The different is because it's different potential. But the general idea we already discussed here. So you know the next job is going to solve the eigenvalue. Okay, good.
Feels like we never left.
Dr. Yu, can I take a photo?
Yeah, here. Okay, so.
All the way back to the same seats.
Well, I will be moving around just so that way I can have a little bit of non-degeneracy in my brain.
Just say it. You don't want to sit near me.
I'll slowly start scooting away.
One seat at a time.
Zane, if you want some degenerates over your head, come learn some E&M with us again.
No, thank you. I did my time. I have enough to learn
You can do my time too.
without learning things over again. But you all are going to do great, aren't you? The E&M, 611. What time is that class? Right now?
After 15 minutes.
Oh,
Oh, after this. Wow.
Yeah.
Okay.
you got
So
this. You guys better get some coffee. Get some coffee, stay awake.
So you all passed last semester. Good.
Fortunately, yeah.
Fortunately, good.
There's
By the way, how
only 2 grades in that class last semester,
okay.
so it was a lot of pressure.
I know.
But now they increased the homework percentage.
Okay.
So instead of 1 times 10 to the negative 27, it's 0.02%.
Okay.
Wait, no.
It's actually 234.
Oh, that's sorry. Even less significant.
I love that he was right there to pop in and correct you.
Yeah.
Is
I stand
this
corrected.
And it actually appears to be 2%.
You just put 0.2.
Gotcha.
Because now the special topic part of it is 18% instead of 20%.